Let's talk about a classic example that's used in conservation of energy and momentum, and it's called the ballistic pendulum. Essentially what happens is, in lab, it's not a gun, it's like this little spring-loaded, kind of like BB gun-ish thing, and it launches a round ball that sticks into the ballistic pendulum. And then the ballistic pendulum is free to swing. And generally there's some sort of latch lever over here that once it's swung as high as it's going to go, it won't fall back down. So we can figure out how high this thing will go. We can measure that. And one of the classic things to ask is, what is the mass of either of these things, or what was the velocity after the impact? There's all sorts of things that we can ask. The things that are generally measurable, it's going to be like when it catches on over here, we'll have some distinct height that we can measure. We know the height of this thing, and sometimes we know the mass of the ball, or sometimes we know the mass of the pendulum itself. It just depends. So we can look at this and let's think about what we have at the different parts and pieces of it. So when this ball first starts moving, let's go in this way. So here it has little mass and some initial velocity. And then when it sticks, at the point where the ball is embedded, let's see it, then I have like little mass plus big mass, plus big mass, and they're going to have some velocity. And then let's see, what am I going to have here? I'm going to have some sort of kinetic energy here. I have kinetic energy here too. So we'll just call this 1 and 2. And when it swings, just as it comes to a rest, let's see, I'm going to have potential energy here and no kinetic. So all my kinetic from the swing is going to go up here, and this will be for little mass plus big mass. Now what's true about these, if you think back to the last two videos, that I have an inelastic collision going on here. So the little ball is going to stick into the swinging thing, and it's going to swing all the way up here. So this is an inelastic collision where I have this combination of masses. So momentum is conserved here, but energy is not. And now it starts to swing. Well, we have like this external force acting on it, don't we? So momentum is not conserved, but energy is. So my external force that's acting on it is the force due to gravity. So we can write this out as a kind of a series of equations. So I can have little mass with its velocity is going to equal then this combination of the masses and some final velocity. Then from the energy picture, I can do something like this. I can say, so I have, let's see, 1/2 mv squared. So this thing is going to have some sort of final velocity. It's going to be the same thing as that. So I have 1/2 m plus big mass v prime squared. In conservation, it's going to go all the way up here, is going to equal little m plus big M, GH. So this one here, that's just mgh, potential energy due to gravity. Make that clear for you. So let's see, can we simplify either of these two things down? And I feel like we can. I can say on this one here, at least, my masses are going to cancel out on both sides. So I'll have 1/2 v prime squared equals gravity times height. And then I can even rewrite that as v prime squared equals 2gh. I can write that down even further. I can go, so v prime equals the square root of 2gh. So when I look over here, like if I wanted to solve for, say, the initial velocity of the ball, one of the things I can do, if this is a measured height, is put the square root in here. So I can say then mass 1, velocity 1 equals little m plus big M times the square root of 2 times gravity times height. And I can go even further. If this is the thing I want to solve for, I can go, so V1 equals mass, little mass plus big mass divided by little mass times the square root of 2gh. That's one thing I could do. If I was somehow able to, I don't know, let's see, if I can measure this height, I can figure out what this is. So I've done that. Or if I can measure velocity instead, which is generally a harder thing to measure, I mean, we'd have to have pretty good time clocks to do that. And so this is probably the most common thing that we go to, is to solve for the initial velocity of that thing. I mean, but then we can also, with the height though, you can see we can get right to how fast this whole system is moving, which is pretty cool. We can do all sorts of things. This is probably one of the more common ways that we will look at conservation of energy with momentum. It's a fun example.